Okay, so all of those terms that we had of this, we had a sigma xx, right? And there's another one that's all compressive forces in the x. There's a sigma yy, all the compressive forces in the y dimension. And then there's a sigma zz, all the compressive forces in the z direction. And then you had these other forces. Right? So these are the 9 components of this giant thing called a Cauchy stress tensor. Right? Right? And that's all of these things. So this is a monster because before we described a vector field, which at every single point in space assigns some velocity, a v, a vector. Then we had scalar fields where every single point, right, assigned a density. This is even worse because this, at every single point in space, assigns a matrix of these 9 components of forces that can occur on some differential tiny little bit of fluid. And that's this term right here is helping you describe the surface forces that happen on the outside of a little bit of fluid, right? So we're just, this horrible thing sometimes is denoted like a big capital T. And then you notice that, right, as this thing happened, if you look at the expressions, you always had these, the only things that remained were the derivatives because the point canceled off in the last calculation. So all of this really just to get across that, really to describe the motion of a body of fluid. It comes from little bits of fluid around it, and you consider the forces happening, where if you had a center, right, you have a center of mass of all your little points of fluid, that, right, the prescription of motion ends up being, right, if I look at all the sum of the forces, oh yeah, we're in per unit volume. Sum of all the forces I can tell, per unit volume. This is for incompressible fluid as well. Now we have some understanding of this, because this is actually going to be body forces, which act on the center of mass of all these for every single point in the body of fluid. So that's something like gravity at every single point of fluid will work like this. And then you have this other term, right, which is the divergence, because it's all derivatives just of every single component of the Cauchy stress tensor. So you tell me body forces, you tell me things about the stress tensor, and I will prescribe the motion of the entire fluid field for you. And that's exactly all fluid equations are getting at that. They're Cauchy stress tensor equations. This is even another simplification I've been doing because I've been saying dv dt, but in reality, momentum, which is the product of the mass times the velocity, is a better statement to make about Newton's second law. I mean, in reality, this is the material derivative of the linear momentum, right? Capital P for, right, linear momentum. That's where integrals come into. So before we move on, I just want to point out that really the fields of fluids come down to assumptions on that stress tensor. Or one way you could think of it, right? So we had all these components. They're all the components. Right? And these are the, you know exactly what these ones are. Okay, so when you hear about viscous fluid flow or inviscid, non-viscous fluid like air or a gas, which the viscosity or the friction of the fluid doesn't really matter much, they can be summarized as just assumptions on the components of this term. Okay, so great examples in your book. So for an inviscid fluid, we just say that all of these tau terms are equal to 0. And then you say that there's just a pressure, some pressure. Right? And this is what we call inviscid. Another description I like, Richard Feynman called this dry fluid. And then for a viscous fluid, you then make an assumption on these shear forces, where you make a Newtonian fluid approximation. You say that compressive force is a negative of the pressure plus this term here. Right? So that, right, and then same for these. Okay, so this part right here is the Newtonian part, where you say that there's some experimental number called viscosity that I can measure, which is a force, right? Which is the rate is a force is proportional to the gradient of the velocity. If you plug this into that stress tensor, you get the viscous equations, or Navier-Stokes equations for a viscous fluid. I don't believe in this class I have to go over the entire derivation of that, but you get some pretty nice looking equations. You could say that you just write in vector form. And this is the vector form of the Navier-Stokes equations for viscous fluids. Where this extra term popped out, right? This extra term pops out from that Cauchy stress tensor and the pressure as well. And these body forces are other things I'll describe next video, just the example of how gravity can be one as well. And then extra credit is just to take these expressions in vector format and then write out every single component of them, which is a good practice example to go from vector expressions, which I like writing because they don't take as long, to write a bunch of equations involving components. And your book just does this for you as well. But extra credit if you want to go from this to 3 equations stating Navier-Stokes equations.